Right, so then the next speaker is again Juri, who is going to tell us about more details of scheduling. Okay?
Okay. Yeah. Since we got a really great introduction by Marco, and also thanks to Peter for the details about CFS, and also because yesterday we actually talked a lot about what is implemented by Scheduling. So the theory, also thanks to Luca, it's all there, so you basically should know what's behind it. I'll try to go and to give you really further details. So yeah, we are going to look at the code. Yeah, so be prepared for it. So we will see how it works. Really. So yeah, just to recap.
Can I interrupt you just? And I just put the presentation online. So.
Actually, yes, the presentation is really minimal because then I use like this. Go to this side to see.
Okay. Yeah, but in the presentation there is that side.
Yeah, that side is on the presentation. So.
Okay.
Okay, so this is what we have, the new scalar framework. So we are going to talk about this deadline.c and stuff that is bound to it. Okay, so you probably remember from yesterday about the interface we have for scheduling. So basically, and also for the other scheduling class, and but basically we adjust this from user space to kernel space. So we have to specify runtime, deadline, time period. So let's start and see how they are.
Should deadline be always less or equal than period?
Sorry?
Should deadline be always equal than period?
Yeah.
Okay.
And also the runtime. Yeah, okay. Yeah, so let's try to start to understand how those things are actually implemented. Okay, so as I said, I'll try to use this sign, go back and forth with my slides. Okay, basically this is the sched class, sched class. So here
the file name.
The file name is on kernel sched deadline.c, and this is how where it is defined. And this is the sched class Marco told you about before. And here you have all the hooks. So the actual function are hooked into the function pointers that are previously declared. And so basically, from here you get the big picture of how these things works, because you have the enqueue task and the queue task, you have the relative enqueue and the queue task BL. Then you have this check preempt curl. This is actually pretty simple for us because we just compare deadlines. So the earliest deadline will preempt the other one. And yeah, pick next, and then you have also the task date curl. That is actually called every schedule routine. And yeah, so this is, and also you have the SMP features that are confined here. Yeah, we'll talk about the SMP later because it's fairly, it's actually a bit more difficult than just this. But anyway, okay. Okay, yeah. Let's see how the. Okay, here in kernel sched.h, you have the struct of the run queues, and as the comment says, you have one of these for CPU. So, and inside of this, let's say main or father run queue, root run queue, you have all the run queues of, for example, CFS, RT, so a sched 5 or sched round robin, and our run queue. So we can actually see how the thing is implemented. Nothing fancy. Actually, we have red black tree ordered by deadlines, and so and that's it, because you have the number of the tasks running, and those two are to be enqueued in the red black tree. And for SMP stuff, we also keep track of the deadline of the current and the next to be that is enqueued on the run queue, just to be fairly fast when deciding what to do on SMP systems. But I will talk about it later, so nothing fancy here. Okay, let's see where the parameters the users specify are handled inside the kernel. Here you have the main task root, as Marcus said, and inside this task root we have several SCADA entities. It's like for the run queue, actually, because you have different entities for different scheduling policy and tasks. And let's see what SCADL entity contains. Okay, here we go. As I said, the tasks are enqueued in the red-black tree of the run queue, so you have basically the node to be able to do this. But the interesting part are these two parts of this struct. Here you have there are like DL runtime, DL deadline period. Those are the original scheduling parameters. So what the user gives you are copied here, basically. So those are the original values. But here you have the actual parameters, because you're going to basically you're going to update these parameters performing scheduling. For example, runtime will be decremented every scheduling tick, for example. The deadline is the deadline you use to actually doing scheduling. So there are the CBS rules. We talk about that tomorrow. Yeah.
Yeah. Sorry for interrupting.
Yeah, sure.
Maybe could help if you explain that the parameters you show above are the capital letters Q and D,
oh, yeah, sure.
while the other are the lowercase letters on the yesterday's presentation,
sure.
so that people can map these on the presentation.
Yeah, sure. Thanks, Luca. He was saying that to explain better, these DL runtime, DL deadline and period, they are the capital QI, or PI and DI that we were talking about tomorrow, so from theory. And those are the normal, the non-capital values, so just to refer to theory. All right, so we'll see how those are handled by the kernel. Okay, I'll talk about this later when I talk about SMP scheduling, because it's a data structure purposely used by that. And I already talked about that. Okay, those are basically the main structure that we use to do all our stuff. Okay. Well, I don't actually. Okay, let's see a bit core functions. I won't go. I won't explain every single function, but those I think are the most interesting. And okay, set up new DL entity. Not surprisingly. Okay, here we go. When you create, so when you set a new reservation, so you call set at, you basically create a new DL task, let's say, and so this is called first time in this before the Q&A, and you see that you use here the original parameters so the capital DI, so the deadline, to actually set the deadline, the actual deadline of the task that will be put on a run queue, and use the run queue clock because it's here. This is a relative deadline, so here you have the absolute deadline, and here you just copy the actual original runtime in the actual runtime, and you just set that is a new entity that will be treated in a special way. So that's yeah, okay. This is pretty simple. Okay, thank you. Okay, not this one. Yeah, this one. Okay, basically, in queuing a task, it calls this. There are like so hence the heels here, and you see that once you enqueue a task, you basically have two possibilities. You will probably have to replenish the entity, and I will explain what it is, or you just update it. Let's say you don't look at this for now, and just say look at the update at the end. What is done inside this function. Okay, and here we we are actually near the CBS roots. So here we see how they are implemented. Because every time you update, this thing is called actually when a task gets back on the run queue. So, for example, we slept for a bit, and then we wake up, and so this thing is called. And if you remember from yesterday, one rule of the CBS is actually applied and checked when a task is queued back in run queue to prevent it to go over its allowed bandwidth. And this thing is performed here in DL entity overflow. Here we go. Yeah, as Luca already mentioned yesterday, the math, so that the formula he was showing yesterday is actually inside the code, and this is the formula. This is actually the formula, because here you have the original parameters, and those are the actual parameters. This is actually translated with two multiplications because the divisions are really are not cheap, but there's nothing really fancy. You just put those things on the left and right, and then just compare them. Use the L time before just the measure sign. So that's it. Really simple, and this is actually the real core of the thing. All right. If you have any question, please ask. I mean, it should be like they tend to be really informal and yeah. Okay, so that is done when you are queued back in the run queue. So you want to check that. But okay, runtime control and is performed at basically at every task tick. Sorry, a schedule tick. And so let's see where this is. Here we go. So this thing, that's this tick DL, is called with hertz frequency. So let's say if you have 100,000 errors every 1 millisecond, this is called. And this basically does update core DL. And here we go. Well, apart from things that not really important, you see that the delta exec is computed, so how much you executed the last over the last time that was called. So you basically execute for clock task is now minus when you started, and this thing is decremented for your current runtime. So basically every milliseconds you got 1 millisecond less of execution time. And here is where we implement the throttling mechanism. Because once you decremented the runtime and you check if you actually exceeded your allowed runtime. And if you actually exceed it, you call this start DL timer that actually sets an HR timer that will expire when you are ready. You will be ready to be replenished. So when you'll be ready to get another original amount of runtime. So, and when this HR timer expires, basically this is the callback for the HR timer, and not surprisingly, it will enqueue back. So when you're stopped, you are dequeued from the DL run queue, and basically you are kept in the HR timer. And when the timer fires, you are enqueued back in the run queue, and you actually notify that replenishment has to be performed by this setting display, passing display to the function. And this will basically replenish the actual runtime of the DL entity, considering also the fact that you can utilize a bit more of the runtime. So it's like this thing is taken into account, and then you reschedule and do whatever you want. Yeah.
Just a question. When you replenish, as I understood you get negative with the budget. You sum the budget again. So your current time becomes negative because you use it too much.
Mm-hmm.
Then you sum
the runtime,
you sum your budget that is specified at the maximum.
Yeah.
So you go positive again and you are enqueued again.
Yeah.
It can happen that when you sum, it is still negative.
Yeah, yeah, sure. Actually, we keep incrementing till we get some positive budget.
So you,
and also the deadline is probably basically
yeah.
Yes, because it depends on sure. Yeah, thanks. Yeah. Okay. Well, I mean,
But what happens if in the code instead the budget is negative? Let's say since the beginning I write a negative number. No, it's unsigned.
Where?
In the runtime.
At the beginning, you can, because the runtime has to be greater than 0. I mean, the user value is checked to be greater than 0. Okay. So, and you use that the first time.
So you are assigned 0. I mean, in case you do. You write negative.
You can actually, it has a minimum value that you have to assign. But yeah, I mean, as Peter probably mentioned yesterday, or we were talking about it, I mean, how much this runtime can be in the low, how much low this time can be, it's kind of problem, because if you assign a really small runtime, you're basically you won't get scheduled, because I mean, the runtime is always decrementing. You finish it before actually doing anything. So yeah, that could be a main problem. But yeah, we should find some good value to check this. Okay, as I was saying, this is pretty much all about uniprocessor systems. Because you basically check the CBS rule when you wake up. You check that you are not going too much over your runtime, and that's basically it. So let's see what happens for SMP systems. And okay, I can probably. Oh. Okay, I already showed this slide yesterday, but just to recap, on SMP system we try to implement what we call global EDF, so global scheduling, and basically you have on an end CPU system the M earliest deadline tasks that are ready are always running, and you want also to respect the finite CPU sets. But since the other tasks are kept into CPU run queues, you have to perform migrations, or as Marco already said before. Let's try to see how this is implemented.
So one detail, often students come to me asking how do we implement global scheduling. I say, well, you can keep a global run queue, and in your big next that put previous functions, just take a global log around your global run queue and do task things.
Yeah.
So you can implement proper global, but it's not queued from a performance point of view. So this approximation to global that you're about to describe performs better because the contention is typically between 2 or maybe 3 CPUs and not all of them.
Yeah. Yeah. Okay. Yeah. Thanks. Sure. Okay. Both SCAD-FIFO and Run Robin and us perform SMP scheduling by doing push and pull type of migration between run queues. Let's try to see also, you've seen this yesterday. Basically, instead of waiting for like time slot or some instant to perform load balancing, you actually try to do load balancing at every instant when something happens. In this case, for example, the activation of this task on a run queue causes migration tasks. So basically, this task is it's actually pushed on some other run queue. So the thing is that when you, okay, let's say before deciding who you want to run, because for example, in this case, you decided CPU to run. You try to see if someone from some other CPU has better chances to be run on my CPU, because, for example, it has an early deadline of the task I will be I'm going to schedule, and this is a pool. So I try to pull the task on my run queue. After I schedule, I try to see if one or more of the tasks that are still ready but not running on my CPU can be pushed on some other CPU to be run, because probably they have an earliest deadline of some of the tasks that are already running on the other CPU. So that's basically the push and pull mechanism, and yeah, this is basically what I already told you. And yeah, this is all nice and fine when you have a small amount of CPUs. But how can you, for example, if you want to perform a push operation, where you will be pushing a task. So how you can know where it's better to push. I mean, it's better to push a task where on the CPU that has the task with the latest deadline, of course, among all running tasks. Okay, but how do you know which is it? If you don't have any specific data structure to know this, you have to perform a global search. So to check every run queue, every deadline of the running task, and then after that you can actually do the push operation. But this is highly costly. So we added another structure that is simple. It is called CPU-BL, and this is there's one of these for every CPU set. So actually, with Linux exclusive actually CPU set. So in Linux you can create this joint set of CPUs. There are like exclusive sets, and you got one of this kind of this structure for each of them, and okay. Here we go. That's basically this thing. It's nothing fancy. It's just a simple maxi and order by deadlines. So in the root, you have the latest deadline among all the running tasks. So when you try to push someone, you basically check two things, because we have that, and we also have a bit mask of the free CPUs. So free for us, I mean, not running any deadline tasks. So you just check that if some CPU is free of deadline task and you push there, or you just check for the root element of the heap, and then try to see. I mean, if you are earlier, if you have an earlier deadline than him, you push there. And this thing, there's a simple, just one row speed lock for the whole structure. But and I mean, we actually perform experiments on like quite big machine, on 48 core machine, and these things did well. I mean, it's not a bottleneck, and also considering that there are also studies that says that it's not a really good idea to go over like a 6 CPU cluster to perform real-time scheduling, because there are like cache effects and everything. These simple things actually works pretty well, and it really win when you have to do this really fast instead of doing the whole loop. Okay. So yes, basically, as I said, it's nothing really. The code is this. I mean, there are all a bunch of old functions really to implement all these things. Those are the main functions that are implemented, but the code was this. And so have you any question on this part? Because actually, next slide tells about what is missing actually. So, any question on what I talk about? Okay. So, what's missing? This is really the real basis for EF and CBS in Linux. So it's just the bare minimum to have something working. And I didn't mention what happens when you have shared resources. We actually have already implemented same thing you have with priority inheritance for fixed priority scheduling. we have deadline inheritance. So instead of inheriting the priority, you just inherit the deadline. But the problem that we have right now with that thing is that when you inherit the deadline, you actually are outside the bandwidth enforcement mechanism. So you can go, I mean, you can ruin all the system, and that's one reason why these things, scale deadline is not, it's just for root users. Because, I mean, and
but then we pay, right?
Sorry?
Then you pay when you're.
Yeah, but it's not like, yeah.
So the deadline will. So you lose your temporalized.
Yes, so you lose.
At least the runtime that you try to use is the same. You will account for it eventually. Yes.
Yeah, but it's not really what we want.
What we want.
Well, what I think we want is really to go over appropriate protocol to deal with this. And there is one that's called multiprocessor bandwidth inheritance. So the basic idea is instead of just inheriting the deadline, you actually inherit the bandwidth. So you actually run with the bandwidth of someone else. But that's open to discussion. But I think to properly implement this, we probably need proxy execution. So you actually have to be able to run as some other task in our case. And yeah, that's a discussion, but it's not a problem just for us. Because also there are also problems with simple priority inheritance for SMP systems, and related to the fact that you related with the CPU affinity thing. So if you restrict certain processor to run on certain CPUs, and those problems, I can refer you to papers by, for example, Bjorn Brandenburg. Should be resolved with proper proxy execution also for static priority tasks. So we can then use that once implemented to properly to implement the multiprocessor bandwidth inheritance. We used to have also group scaling support, and it is now removed from the core that we have in Linux. So we patches are already there. So then we be able to scale a group of tasks in the same reservation. More than group scaling would be really nice to have hierarchical scaling. So you can then use a scale deadline reservation to scale with whichever type of task you have. For example, scale FIFO tasks. So you have both goods of both worlds. And then, more fancy things like bandwidth reclaiming, so you can then be able to donate exceeding bandwidth, so the bandwidth that you are not using, for example, because you stopped before you are allowed to run time, to other tasks in the system to be able to cope with stranger and effects. Right, so yeah, that's basically all. And I wanted to go in the code details because in the hands-on session of this afternoon, we'll be back on the code and try to play a bit with it, see how, I don't know, you can extract information and let's say debug it. Because actually all this workshop was also intended to try to get people also involved in the development of this stuff. So yes, that's it. Oh, because there's this Juniper European project, it is actually not only paying for the coffee breaks and all this stuff, but also the last part of the development of this thing is on the Juniper project. So yeah.
If you have interest, of course, let Juri and everybody.
Yeah.
Okay. Thank you, Juri. Questions for Juri? Yeah, about this or yeah.
Here, I see that one question. We talked yesterday at the theoretical and then also reading the documentation, talking about how tasks that you know are going to be periodic can let the scheduler know it's going to go to sleep versus how you handle aperiodic tasks. Mm-hmm. Is that anything that bubbles up to user space, or is that totally handled?
No, it's totally handled by the scheduler, so the kernel. Basically, it's the two. I mean, there are the two rules of the CVS. So one's the throttling mechanism, and the other thing that I show you with the DL overflow. They basically can handle that.
Well, there is a deadline schedule.
Sorry, second.
There is a scheduled implementation for.
Yeah, yeah, sure.
Basically, wait for you to current. Says I'm done, and then we have to finish it.
Yeah, okay. I'll just repeat that because probably for the public, but as Peter, yeah, I was saying there's also the sched yield with which you can signal you are done. So you are like put to sleep until the next period. So
Best practice going forward with something like this would be your user. This would be one in case you're not thinking it's not.
Because there's and I think schedule will be required for CPU reclaim.
Yeah.
Because otherwise we don't know you're actually done. But yeah, that's all I do.
Yeah.
Thanks.
Yeah.
I don't know what
I have a question about affinity.
Mm-hmm.
That you say that affinity are respected, and how could you do a global decision? Well, if two tasks have different affinities, then the new task preempt the one running, and but the one running is not the one with earliest.
Yeah, actually, yeah.
Or then you.
Yeah, sure. You're right. One thing that I didn't mention is that the only way with sched deadline to actually create affinities is just using CPU sets. So actually, you are not allowed to set an affinity lower, smaller than the whole mask of your CPU set. So you don't have that kind of problem. You have to create a CPU set. In the case you want to do partition scheduling, you create a CPU set corresponding to one to each CPU.
More like
different.
a cluster idea.
Yeah, it's like cluster idea.
Yeah, that's because we couldn't solve the actual.
But yeah, just curious.
I think it's
Also
a
admission
fundamental
control.
problem that you start to.
So yeah, and that's one of the issues that I don't know how to deal with putting RT as FIFO and real round robin tasks in a sched deadline server, because people are accustomed and expect sched set affinity to work.
Yeah.
But we can't. So I'm not sure how we're going to do that.
Yeah.
Oh yeah. Okay. Thank you.